in the sense that we had a discussion with several of the participants here, and so what was conveyed is that while each step may be followable by all of you, somehow the way of reasoning, the background, whatever, to probability theory is not so well known to everybody here. So, as a result, I have decided to make this lecture, something on the elements of probability theory, and we will just start anew, afresh, and we will keep referring to some of the results we already derived in this context. Okay, so, I mean, if you wanted a title for this, I'd say elements of probability. And you will find this in, of course, textbooks here and there. But I mean, I have just tried to go through in my mind in some fashion, largely guided also by the material we have covered in the first two lectures. So again, I have numbered some points, and just so that you know, the lecture will end. Unfortunately, there are quite a few points, but they will be covered rapidly. There are 17. Okay. But they are not all exactly equally long. There is a mean value and there is a spread. Okay, right. So, first thing, let me define what I should have done right in the beginning. So, people usually talk about random variables. I want to talk about a random event. Something may happen, it may not happen. So, a random event E is one whose occurrence cannot be predicted with certainty. And of course, we have many examples of this in the context of the models we have been dealing with. The first step of a random walk cannot be predicted with certainty. There is a certain probability of moving right, there is a certain probability of moving left. It may be equal, it may not be equal, but so the event could be the random walker moves right. That is the event. Okay, but we cannot say for certain that will happen. So, that's all. So, this is the notion of a random event. Whenever you are discussing any problem in probability, it is very good to be very clear about what is the event that we want to find out about, whatever. As I said, in the random walk context, it could be this, slightly more involved question, again still within the random walk language, is what is the probability that I will be at the next site after 5 steps. So, that is certainly not the same as the probability of being at that site after 1 step, because there are more possibilities, but the event should be clear in your mind. Okay, so that is number 1 over. Number 2. Ascribe a probability perhaps 1 and 2 should have been done together, to the occurrence of event E. All right. If there are several options, and of course there are, if there are options for an event E1 to happen or an event E2 to happen up to an event En to happen, these are mutually exclusive events. This is a familiar phrase that is often used, so I am just using it, but I will just tell you in a minute. In other words, if this happens, this cannot happen, the rest cannot happen. If one happens, the other can't. For instance, in the random walk sense, suppose E1 and E2 are two events. One, random walk moves right. Other event, quite distinct event, random walk moves left. The events have something in common. In both cases, the random walker has moved one step. Modulus is 1. But that is besides the point. The events are distinct. Okay? If one happens, the other can't, because they are distinct events. With probability, and there you have a certain with a prescribed probabilities P1, P2 up to Pn, and that's all. Then can you say something about the P's?
They should be greater than 0.
Correct. So this is the first thing. Then each P is greater than or equal to 0. Could be equal. It could be that something is impossible, in which case it won't happen. And the sum must be 1. Yeah. So if I sum over all options, I should get 1. So far, so good, right? Makes sense. I mean, I hope it makes sense. If something doesn't make sense, interrupt. Okay. All right. So let's give some examples. You have a die. It's Shamik, so we say die, right? For it's spelled D-I-C-E, a single die. Or D-I-E or D-I-C-E? With the C, right? With the C. Of course, D-I-E without the C is also die. But let's. I believe it's with a C, but I wasn't sure, so therefore I consulted. Okay. Things are possibly checked on internet, but after class. So I won't say what it is, this object. So a canonical die has how many faces? 6. Because it's a simple cube. You can imagine more complicated dies, icosahedra or something, but we won't. So there's 1, 2, up to 6. There are 6 faces. Each of them have dots, the corresponding number of dots. And they are very good for playing games. You'll play Ludo or something, snakes and ladders. These are the games you should play. Let's say, suppose we have a die, and it's a fair die. So all, you understand. So there exists 6 options, and all occur with, let's say, with the same probability. So what would the probability be in this case? 1 by 6. This is one example. Second, let's say we have an unfair coin. So somebody has doctored a coin so that it will end up one way or the other, but not doctored it in a very obvious manner. Otherwise, it will show up immediately. So let's say the coin has options heads and tails with respective probabilities 0.51 and 0.9. 1 minus 0.51. Okay. So these are two possibilities. So, given these things, we can always think in terms of probability distributions. What is a probability distribution? So, let us think about the distributions, and in fact, let us draw them or sketch them, sorry, and you can move it out. So, a probability distribution is a function which shows the probabilities of various events. For instance, let us think about this die. Okay. All right. No, so what we will do is we will not talk about the die per se, but we have said this. So, let us imagine in fact, so a grasshopper will make steps of lights or whatever, make steps of length 1, 2 or 3, or for that matter -1, I mean of course, I should say make steps with displacements. With equal probability. So, that grasshopper would be well advised to carry a die in its pocket. So, it can just spin, okay. And depending on 1, 2, 3, 4, 5, 6, there could be a 1-to-1 mapping between what comes on the die and the possible steps. So, for instance, what would the probability distribution look like in this case? So, we have 1, we have 2, 3, 4, etc., -1. We are talking about the probability distribution of a given step, right. Well, it should be 1/6, you will agree. So, here is the probability. So, it will be 1/6, but at where? Well, so let us draw something like a histogram, something of length half this side, that half that side, then another one for 2, another one for 3, and nothing for 4, 5, 6, because those are probability 0. Likewise, we will draw nothing for 0, we will draw something here, etc. So, this is an example of a probability distribution. Just a small word, often in the mathematical texts, they prefer to talk about the cumulative distribution, meaning the distribution up to that point, in which case the probability cumulative distribution would be 1/6 here, it would be 1/3 by the time you come here, 1/6 plus 1/6, etc., etc., and then it will be 1 beyond that. So, you get a series of jumps. So, small exercise, just plot the cumulative distribution that corresponds to this. At 0, it will not increase. So, draw it faithfully, because there is nothing at 0. So, I hope this graph is, the plot is clear. We have something here, nothing here, and something's there. Okay. Likewise, if we looked at that unfair coin, transcribe it to random walk language, what we will say is that the walker will move right with probability 0.51, move left with probability 0.49. Suppose we do that. Is this a fair assignment? It is possible. So, the walker will carry that biased coin in the pocket, keep tossing, see what is the outcome and decide what to do. So, in this case, the probability distribution so there's a possibility of going one step forward or backward, but these are not equal, the probabilities. So, the going forward is slightly more likely than going backward. Okay, so this is to show there is a difference. You can see one is taller than the other. All right. Of course, we could ask in either case, what is the average step length? Now, when we talk about average, we are talking about in our minds repeating the experiment or the experiment in the sense that we are allowing for even one or the other option many times, and then we are taking suppose in this case we are recording how many times the walker moved right, how many times the walker moved left. Okay, we add the numbers up and divide by the total number of trials. So, average in that sense. So, for instance, in the first example, maybe we just move here. So, we are still referring to example A. We are referring now to example A, and we ask what is the average value of n, n being the length of the step. N could be -1, -2, -3, 1, 2, 3. Okay. So, how would you find it? Well, it is the sum over n, okay, of the value of n multiplied by the probability of having that of that value p n. This, it's important to understand this very well. Is this, I mean, what we are saying is that there are various options n equal to 1, 2, 3. When it is 1, we get the value 1, but with what probability? With the probability p1. When it is 2, what is the probability? p2. So, we give a weight, W-E-I-G-H-T, weight, that weight to each option, then we add them up, and that gives us the average value. So, in this case, yes. No, this is here right now a step length. A grasshopper makes steps with of length 1, 2, 3, but it can make it in either direction.
Index is also n.
Sorry?
Index is also n.
Oh, yeah, it is, but is that wrong?
No, in this particular case, both are integers. Value and the step number, they happen to be the same.
Okay, let me proceed until confusion hits me. Okay, at that point I will go back and change everything. Right now it seems okay to me. I mean, yeah. Of course, the average value of n need not be an integer. Average of 1 and 2 is not an integer, for instance, but in this case it is an integer for the, so this is a general definition, but when I plug in, I will be plugging in 1 times p1, but there is also a -1 times p with the same probability. So, I will get 0. So, in that example n equals 0. It is a symmetric distribution. Question, quick question. If n is, average n is 0, does the distribution have to be symmetric? No. You can cook up and easily imagine many distributions which have mean 0, but which are not symmetric. All right. Okay, good. So far so good. But likewise, we can calculate average n squared, right? Or anything. How would we do it? With the sum over n, multiply n squared by Pn and get what we get. So, let us just do it longhand. Okay, so we get 1 squared when the step is 1, we get 2 squared when the step is 2, but they are equal probability, that is why, okay, so 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 and the same thing repeated when I go minus 1, minus 2, minus 3. So, I get 2 times this. So, you can do this bit of calculation, just arithmetic I should say, and just check, because I am not totally sure, but it is 14 by 3. Okay, so this is the way you will calculate. Well, if you wanted some other function of n, like n to the 4, you could do it in the same way. Suppose you wanted e raised to n, I mean average of e raised to n. How would you do it? You just put in this e raised to n times Pn and just evaluate. I mean, or you know, any function of n. Okay. What about in example B? Average n this time is not 0. Okay, so what is it? This is step length 1 with probability 0.51. There is a step length minus 1 with probability 0.49, and this turns out to be 0.02. So, the average value of n in this case is 0.02. What will it mean? Actually, the guy goes only one step 1 or minus 1. What is the 0.02? If you repeat many times and you take the average, then this is the small bias going forward, to go forward rather than back. Okay so far? Okay, good. Well, we can evaluate n squared again, and that is very easy to do. It is 1 times 0.5 plus 1 times 0.5, 0.51 plus 1 times 0.49. This is a multiplier, this is 1. Right? It is also important and instructive and everything to evaluate sigma squared, which is defined as n squared minus n average squared, which is 1 minus 0.02 the whole squared, which with an appropriate number of 9s will end with 6. Agreed? Okay. How would you find sigma? Can somebody quickly estimate sigma? Take a square root, and the answer is the square root of all this, but how would you evaluate the square root quickly? 1 minus exactly, this is 0.0 something 4. So, you do a binomial expansion and you conclude that this will be 0.9998. Of course, not exactly, there is some correction there, but fine. Okay, so this is just to give you some quick grounding. Okay, now we are ready to go further to point number 4. I told you the points are not equally long. Yes.
By knowing average n or n squared, I have some physical idea about the distribution.
Yes, yes.
Sigma square tells us.
Sigma square actually tells you more than average n squared tells you. What it tells you is about the width of the distribution around the average. Okay. So, let us say you had a distribution which looked like this. So, here is 0, okay, this is the distribution. Average n will be somewhere here probably, I mean maybe a little to the left, I guess here. This is average n. Average n squared or the square root of that will also be somewhere there. But what sigma is telling you is around this mean, how broad is this distribution? So, sigma or 2 sigma is telling you that. So, sigma is accounting for the shift because of the mean, Because the mean may be very, very big, but you want to know how broad is the distribution. Just because the mean is big, average n squared will also be big. But that is not what you want. What you want is to know something about the distribution, and it's telling you how wide is the distribution. So sigma is very important because of that. Oh yeah, we should do it. Right. So indeed, so sigma squared, you notice, is n squared minus n average squared, the way we have defined it. But this is identically equal to, and this is very important, n minus n average, the whole squared average. How do you prove this? Complete this, just expand, and you will find that you can prove it. But in this form, it makes it very clear. It's how much n is deviating from average n. Okay, is this good? Thank you. Yeah, please interject with words of wisdom or otherwise. It's right. Mean square of the deviation. Exactly. Sigma squared is the mean square of the deviation. Yeah, you might be tempted to take n minus n average. You don't like powers. Now, if you just do this, it will be 0, but if you want to not take powers, then please put a modulus. To find the modulus, you will have to square and take a square root. So, better just do the square. Okay. All right. Yes? No? Okay. All right. So, we finished point number 4. No, we've finished point number 3. Point number 4. Probability distribution. So, by the way, yes, what was it? Any question? No, they will not be equal, but it will be a measure. It is another measure. No. Indeed. Now, so probability distribution for a continuously, is this okay as an abbreviation for continuously varying variable? Varying variable? Okay. All right. Or continuous variable. Okay. Continuously varying variable. Actually, this sounds good. A varying variable. All right. You can put changing. Fine. Then, I just want to discuss it. So, here we are. We have a variable little x, which is a continuous function. It's my step length, because I am, not regimented to take exactly 1 meter steps or whatever. I can take steps of any size as per my whim. So, if I do that, I will have a distribution which looks like this. Some distribution. I need not be symmetric, something like this. What is the meaning of this distribution? What it means is that if I take a particular value of x, say x naught, and I consider a small delta x or dx, I am not distinguishing, interval there, then px naught dx will tell me the actual probability. It's the probability, is the probability to be or to have x between x naught and x naught plus dx. Okay, so to find the probability in this case, we have to look at the area under this strip. And we can add up all the areas and we will get 1, of course, but this is, therefore, P of x is not a probability, it is a probability density. Therefore, Px, so let me change the word probability distribution here to probability density. So, density, as you can imagine, tells you this is it. The cumulative probability is like the density up to there. That is what the mathematicians prefer. Somehow, I think most physicists think intuitively in terms of density. This is more probable than that. You know, why bother to integrate up to here and then up to there and then ask, you know. So, we could do that. All right. So from now on, I will deal with probability densities. Yes.
Because we are very familiar with mass distribution, fattiness and streak. So many times in literature, discrete functions are called probability mass functions, and those are called probability density.
Oh, okay. I didn't know this, but that's a good distinction to make. Right. All right. Good. Sorry. Okay. Let me repeat that. Yes. So, given a probability density, we can always define a cumulative function. Cumulative probability, let me just call it. And I've forgotten the standard notation. I'll just call it capital sigma. What is it called? Capital F. Or is it the reverse? They use small f for this. So capital F for that. Okay. Is the probability capital F of x is the integral minus infinity to x dx prime, that probability density. So, it is the integral up to there, right, that is all. So, the area under this curve up to this point will be capital F x, and obviously then P of x is given by df by dx. Now, this is important, df by dx. So, does it make sense? Of course, in terms of areas under curves it makes sense, but let us interpret it in the way we do, that if there is something that is, if you are looking for an event and you are asking what is the probability that that event will happen between x and x plus dx, that it will happen then. Well, what you need to do is you look at the possibility that the event happens, the cumulative probability up to point x naught plus dx, and of course, it is a little different from the cumulative probability up to x naught, which is larger here. Clearly, this is larger than that. So, if you subtract, that must be the probability that something happened then, because this is what we will use, or we did use in the last lecture for, in terms of some probability distribution. So, just keep this in mind. Okay. Yes.
Maybe one can say that in words, prob x less than equal to
Yeah. So, prob. Yeah, just call out what
x is small x
less than or equal to.
capital X. No, the definition of fx, I mean in words that
Okay.
you have to write some
You mean for this fx is the probability of the event
less than
of the event that x, the variable has a value less than or equal to x. That's what it is. So it's an event again, except it's an all-encompassing event up to x, right? It's not at x, up to x. So it depends on how you define your. So up less than or equal to means up to that value. Do we have any question? Okay, sorry. Okay, fine. Which point was that? Number 4. Number 5. Okay, I forgot to say that of course normalization will imply that minus infinity to infinity dx px equals 1, which will be in capital F language. Capital F, what is the left hand side? F of infinity. So it's the probability that the variable has a value less than or equal to infinity, which is bound to be the case. So that is 1. So this statement is tantamount to that. Okay, it's a question of language. Get used to both. Okay, so I'm rubbing this out. Okay, this is long past. Okay, so a few things that follow from the definition of a probability distribution. Okay, attributes. Of probability distributions. For instance, suppose we have a distribution which looks like that. I mean, okay, let's say it dies down quite quickly, but it looks like that, and not trying to make it symmetric. Okay. In fact, let's make it pronounced. Yeah, it's sort of quite clear it's not symmetric, right? Okay. What is the most probable value of x for this distribution? The peak. The peak. Why? Because this is giving you the probability. When you say most probable, it's the highest one. So this is the most probable value. So that has a name, no? It's called mode. I mean, those who know. I mean, this is called the mode or most probable value. There's also the average value after all, right? I mean, the average value will be somewhere. Okay, so let us say this is like this. And it's not so bad here, it's here. Okay, before the average value. There's also a median. What is the median? Median, okay, so, okay, perhaps I should just put down the definitions. Average value, then variance, mode, median. I'll stop at that. There might be more. So the most probable value of the mode will be dp by dx equals 0 at that point. Of course, you could have more than one, let's leave that out for this distribution. Where p is maximum. That's the most probable value. Median means it divides your curve into equal areas on left and right. That means there are as many events, I mean, or as much probability to do with the events on the left as there is to the right. It's like sort of standing there. In this curve, where would the median be? So here is the most probable value. Will it be to the left or to the right? Right, because if we put it here, the area under this curve is smaller than the area than there. We'll have to shift it right so that it becomes more or less equal. So let's say the median is here. This is a fair guess for the median. Right? Now, where do you think the average would be? Median has put equal, notice that I've purposely drawn a very long tail. So, on the right of the median. So, the average will be somewhere here typically. These are all guesses, but for this curve, this is the average, this is the median, this is the most, why am I labeling it twice? Most probable. More? Oh, more colors. Oh, here. Thank you. Very good, very good. Oh, excellent. Thank you. I'll immediately color the average yellow. Okay, so is this distinction clear? At the median. Yeah, capital F is a half at the median. So, the integral from minus infinity to median of Px dx equals integral from median to infinity of Px dx. See, in practice, mean is very sensitive to outliers. What is an outlier? An outlier is if you are taking data, you suddenly get some slightly out of the way thing which is far away. Okay. The mean will shift immediately in response, but the median will not shift so much. It will not shift at all actually if you just make one value large. So, the median is sort of I am not advocating that you always use median, in a measurement, but I am just telling you the properties. If you use median, it will not be so sensitive to the value at the outliers. The mean will be quite sensitive. Sensitive is sensitive, you have to deal with it, but I am just pointing out the differences between these. Median, mean sound similar, but they are not.
Median also takes care of the probability of area.
Which one?
Median also takes care that what is the weight.
Yeah.
Far away, but what height is that? Because it is area.
True. Yeah. Okay. All right. Yes. Yes. Not just the value. That's right. No, but what I meant is that suppose you take data and you find this point here, this point there. This is some, and you have to take you have to judge. What is it doing? All this, and you only have one point there. The mean will be very sensitive to this last point, and it will shift. Median will not care whether this point is here or there.
Median will care if the height is there also.
No, these are single points. Suppose you made measurements and you had these single points. Yeah. Okay, let's proceed. Yeah. Okay, I should keep some eye on the time. By the way, the coordinator has declared that I have 15 more minutes because of the photograph. So, please, keep patience. Okay. Yes.
So if it's going to point out that this the mode, it's the typical value because why that
Yeah, so often you will find the word typical used. What is the typical value of something? Typical. Well, so you could, for instance, use the mode as a good what should I say, good representation of typical. Maybe median also, no, median, no, I'll take that back. Yeah, probably the most probable value is, yeah, it's the most probable, but is it typical?
Yeah, if I do the experiment 500 times, most likely more often than not I'll get this value than any other value. So that's
Okay, all right.
and the fact that
Than any other value, but yeah, but okay. All right, fine. We will stick to that.
There is an example that I know, that like the difference between typical and average.
Huh.
So one example is that if you buy a lottery ticket, if people buy lottery tickets, typically people don't win, but the average is not zero. So typical is zero,
Right,
but
right.
the average is not zero. Because there is one outlier, somebody must be winning.
Yes.
So that pulls the
That's right.
the mean to some non-zero value. The typical value is zero.
Yes, good. So we should actually, our minds always distinguish between this and recall that what fellow said, people have this mistaken law of averages. That's, so on average, so maybe this average will land on me, or, I mean, it doesn't work like that. So, and maybe if I, do the lottery 10 times, on average I should get it at least once. You have to look at the event space and, what are the possibilities and so on. But thank you, that's a very good example. Okay, now next, familiar or famous distributions. The most important of all, I think, is the Gaussian or the normal distribution, often described in books as bell-shaped. I mean, depends on the bell, but okay, yes. Right. Right. So Gaussian or normal, as it's called. So you can parameterize it like this: 1 over root 2 pi sigma e to the minus sigma squared over, so x squared over 2 sigma squared. Or if there is a non-zero mean, then it would be 1 over root 2 pi sigma e to the minus x minus its average value squared over 2 sigma squared. So you see, we have subtracted of the average value, and the spread is of order sigma squared. So this is what we were saying. Sigma squared is a measure of the spread. So this would be proportional to sigma.
Sigma square is called variance or sigma is called?
Actually, I am not sure. Sigma squared, okay. Yeah. Oh, sigma is called standard deviation. Fine. Sigma squared is the variance. Thank you. Right. Then you could have a distribution which decays exponentially, for instance. I mean, sorry, I am trying to draw an exponential. It's a rapid decay. This is x, this is p of x, and we may parameterize it by some lambda, so e to the minus lambda x. But it should be normalized, right? It should be normalized because integral dx px should be 1, and let us say this is only at the positive values of x, 0 to infinity. Well, the normalization is such that if you put in a lambda in front, it is normalized. Okay. Now, which decays faster at large x, this or that? Gaussian. That decays as e to the minus x squared. Put in a value in your head just like that. X equal to, let us say, 10, e to the minus 10, still within our realm of imagination. Okay. But e to the minus 100, okay, That's way out, that's 0. So this decays, it decays quite fast, it's an exponential, but this is much faster. Can anything decay faster than a Gaussian? Of course. Yes? Yeah, with n bigger than 2. Yeah, sure. Or you could even have a distribution which is cut off and 0 beyond something. So, sure. Yes. All right. Okay, so I mean, I'm not going to put in many more distributions. Okay. But what is the use of a distribution? As we said, important, no matter what the distribution, it helps you to calculate, of course, the average value and all that, but it helps you to calculate anything. Suppose you have some quantity A which depends on x. What is the average value of A? Can somebody tell me? Loud? Yeah, exactly. So, the average value of A will be the integral dx px ax. Does that make sense? Because at a value x, you have the value capital A, but you should weight it by the probability of occurrence of that value of x, and that is what you are doing. So, this is what it is. Likewise, you can. Okay, number 7. Remember, we have to reach 17. Okay. So, like when people give talks, they often write slide 7 of 24 or something. Is that a good idea or a bad idea? I mean, bad. One should not. Oh, I should not have. Okay, right. Yeah, but even I agree it's a bad idea. Otherwise, the whole concentration is on that number. You know, right? Yes. But I have actually heard a colloquium, 1 hour colloquium with more than 250 slides. Of course, it was supposed to be a 1 hour colloquium, let me just say. A very well known scientist from India, and but it was rather fast, I mean, I have to say. Yeah. Anyway, let's go next. Distributions, okay. Number 7. Interesting things happen, interesting effects when we combine random variables. And ask for the probability distribution of the combination. Meaning, we have a random variable x, but we will consider many samplings of x and we will combine them. What is the simplest thing we can do to combine? We could take x1 plus x2 plus x3 plus xn. This is one way of combining, and we will call the result capital X. Or we could decide we don't want that, we want, okay, let us call it again capital X hat, x1 minus x2 plus x3, given n is even, it will be minus xn, alternating. Or we might take a completely different variable and we multiply the x's, x1, x2. And we could ask in each case, what is the probability distribution of the composite variable? Are we in a position to say Well, so then we have to make an assumption that these are indeed independent, but in the case that they're independent and they're independent drawings from some distribution, these are perfectly valid questions. Now the first one, the first question we should ask in any of these cases is, how does the composite variable scale with n? N being this n, so this is important. I'm just saying, the answer will depend on the answer. There's no outright answer. The answer even for that question of how does it scale with n depends on your probability distribution P of x. Okay. All right. So maybe this is all I want to say here. Yeah. So just to make contact with things that we discussed earlier, this was the question we asked when we discussed the central limit theorem. We have a sum of random variables and we asked how is the sum distributed. When we had some P of x that maybe looked like this. Now, okay, so let me write this in this form. P of x equals half into delta of x minus a plus delta of x plus a. Is it clear to everybody that this actually represents two possible values? It's like going back to the discrete case. If we are so steeped in continuum and we just talk about P of x, then if we want to recover the discrete case, this is what we have to write. This is the same as saying that the step could be either a or minus a. All right. No, so for instance, in this case, which is the familiar old first lecture starting random walk, we could ask how is capital P of x distributed? And the answer we worked out, it's a Gaussian. Okay. And this was the content really, beginnings of, or glimmer of the central limit theorem. Okay. Suppose we have the same distribution, we ask for probability of x hat. Who can tell me the answer? Gaussian again. Why? Because the chance, you called it minus x2. The x2 could have been plus or minus some value. Both are equally likely. So this change is irrelevant. This will be distributed the same way as this. Is this point clear? Simply because x or minus x both have the same probability distribution. This of course will not be distributed the same way. How would you approach a problem like this? Take a log. Yes, when you have a product, take a log. So what would you get? You'd get log y is log x1 plus log x2 plus log xn. So we know when we draw x, a given value of x, so let's call these in fact y1 plus y2 plus yn. When you draw a given value of x, that comes in with the weight p of x. When you draw a given value of y, with what weight will it come in? So given a y, there is a certain function of x that, okay. So right, so when we have x, we draw it with probability density px. I am asking, when you have y, what is the probability density of p hat? Let me call it, just in case it's not the same. It won't be the same as p. Yes? Y is a function of x. So you might think that this was, so this, the first question is this just p hat of y of x? The answer is no, because you have to pay attention to dy and dx. So, the point being something like this, that if you have a probability distribution P of x and that so let us say this x maps onto this y, dx will map onto some slightly different value dy. The area under this curve must be the area under the y curve. Why? Because those are the successes. Those are what we are counting for probability. Probability successes. So, these are the ones that matter. They will, so, some other function will come in here. The area better be the same here. Therefore, we must have Px dx equals P hat y dy. The areas must match. So, therefore, P hat y is Px divided by dy dx. There is a modulus, because whether it is increasing or decreasing is not the point. Area numerical is what you need. Remember this, otherwise you will stumble. Dx, sorry? Px dx, yeah. Thank you. So let me move it. Yeah. Remember this. So you can do it when this is a log. So the answer here is question mark no. It's this divided by okay, so P hat of, well, okay, all said and done, P hat of y is Px divided by dy dx. Okay, you can work it out for the log, let me just say. Sorry? Mod x, you are saying dy by dx is 1 over x, so this comes on top, so this becomes mod x px. Okay, good. In our example of the log. Now, if you translate back to y, it becomes a very nice distribution. It is known as the log normal distribution, and it has some very fascinating properties which I will not get into in this lecture in view of the time, but it's a nice function. You should figure out, okay, exercise, how fast does the log normal distribution decay compared to a power law? Is it faster or slower than a power? By the way, which decays faster, a power law or exponential? Exponential we have there, power law. Which decays faster? No. Exponential. Decays means go to infinity. We are not talking about something here. So, power law will be, I mean, just for comparison, I don't want to mess this up, but it will be some sort of slow decay. Power laws are slow decays. You have two power laws, one is bigger, one is smaller. Which will decay faster? 1 over x cubed or 1 over x squared? 1 over x cubed will decay faster because x grows faster, so 1 over x cubed will fall faster. So you have to get used to a little bit of that. Now I am asking you work out this thing. So the answer will turn out to be something, some function, mild function of y, but minus log y squared over some other thing. Okay, so this is the form of the log norm. So where is the y in front? It's 1 over y, right? Weber? Is the y 1 over y? 1 over y. So it's of this form. Okay, all right. Good. So this is fine. This is just some transformations between probability distributions. Okay. Number 8, 17. Okay, so let's look at the case of the sum in some detail. Xn equal to x1 plus x2 plus xn. Okay, so as an example, let's just consider two variables, n equal to 2 and discrete variables. Okay, so that discrete means you can put down the possible values 0, 1, 2, 3, 4, minus 1, minus 2. Okay, so each of these are discrete, and we are asking what is the, so let's say they're discrete and can take on various discrete values with certain probability. So here I'm drawing the probability distribution, including 0. Okay, so is this clear? The area under each is the probability. The sum of these is 1. And I'm asking, however, not for any one of them, but I'm asking, let's say, 2 of them, and I want to add up to some target value, which is, let's say, this one. Okay, just to have a target. This is my target value for the sum. So target value means capital X equals x1 plus x2. I'm still using x, but realize they're discrete. And I want to add up to 3. How can I do it? Well, there are many ways, of course. I could have this and this and this will give me 3. But I could have had this and then this. Or I could have had, you can sort of go wild in thinking I could have had this and that. So many things you could have had, right? So there are many possibilities. So our aim is to find P2 of capital X. In other words, capital X is this plus this. It is also discrete, but we need to find out what is its value. I mean, what is the probability distribution for having different values of capital X? That is the problem. So many ways to reach X. Each is valid, but the probabilities differ. Add up the weights for each option. So for instance, here let us see. To go from this way and that way, I should take P of 2, this one, and multiply it by P of 1. So I should add this. If I wanted this option, I won't get the same weight. It will be this, my P of minus 2, multiplied by P of 3, which is quite, so there are different weightages associated with each. Is this clear? You have to add them up. Okay. So how would you do it? You can do it, of course, but the way to do it is, of course, to add up x1 and x2 with the weights P of x1 and x2, but those x1 and x2 which add up, so therefore we put a Kronecker delta. Are you all familiar with Kronecker delta? It's a capital delta which is 1 when the argument is 0 and it's 0 otherwise. Now why did I do this? So the Kronecker delta is a very nice thing to introduce because mostly it's 0. So it doesn't count, it gives you 0 for those x1s and x2s which don't add up to a capital X. The event you want is that x1 plus x2 should equal x, capital X. So to get capital X, you must have x1 and x2, in which case you want to count that event. Event is distinct paths which lead to this. So the event, if you like, is the set x1 and x2. Am I making sense? Yeah. That's right. No. So we are assuming we are talking about random flights, for instance. So this is in the context of random flights. You're right. So this, but please look at the structure here. You are summing over all possibilities, but you are picking out the ones that you want. Similarly, for n variables, p n of x, sum over x1, x2 up till xn, p x1, p x2 up to pxn, delta Kronecker delta of x minus x1 plus in bracket plus x2 up to xn. So, this does it for you. Counts all the complexions, if you like, of the x's which add up to this. Generalizing further to the case of a probability density, p n x will equal, well, sums become integrals, that is all, and Kroneckers become delta functions, finished. dx1, dx2, dxn, px1 up to pxn, delta function of capital X minus summation xi. It is very important that you understand this equation. It is saying that we are counting properly those events that we want. What are the events we want? We want the events that contribute to a given value of capital X. In order to contribute to that value of capital X, these small x's must have all conspired to add up to that value of capital X. If they do, we take it. If they don't, we don't. So, this is the generalization in the continuous function case of the discrete Kronecker delta form.
In that case, now this capital N, the significance of this capital N now in the continuous limit, it is again still we are looking for N.
We are looking for n. N is discrete and finite. It could be 2, it could be 3, but n is discrete. X is continuous, right? Okay. This sigma x? So this is the same as x1 plus x2 plus xn. So, I equal to 1 to n. Okay, so let us recall. Suppose n is 3. Capital N need not be very big or anything. Capital N is some finite number, or even 2. Here is what we did with 2 variables. So, now if we had 3, we would put in px3 and delta of capital X minus x1 minus x2 minus x3. In continuous, basically what we are asking for is a probability density. So, this is the capital X axis, and we want something that lands between capital X and capital X plus dx. That density. Okay. Capital Px, capital P of capital X is a probability density, and this is the way you will get it. I mean, if you like, we will go through a proof by making it discrete and so on, but let me not. So, more generally, we are getting to this idea from here, from this Kronecker delta, of an indicator function. As the name suggests, an indicator function indicates. It indicates whether a particular event is happening. That is the whole point. Be clear on the event. Once you know what the event is, then good, you ask for the number of ways that event can occur if you want to, if you have to do that. Give the proper weightage, but make sure that that event and only that event is counted. So, in a general case, I mean, it is just a simple generalization, but let me just do it. So, this is something, okay, this is point number 9 now. So, we have crossed the halfway mark or not? Yes, we are now crossing. Okay, 9. 9. So, indicator function. So, what is this indicator function? As I said, it indicates whether the event is there or not. I mean, has it occurred or not. So, let us say it is 1 if the event occurs. We are going back to discrete possibilities, 0 otherwise. Okay. So, as we said, for instance, what is an example of an event? Event is that we land up at a value capital X after 3 steps. That is an example, or it could be something else. Am I clear? Okay. So, if we define eta, some eta for an event, for the event that we like, then the average value of eta will be what? Then the average value is the probability that the event occurs. Think about it for a minute. How do you find the probability value of anything? We have the probability value of A. Well, so we have to sum over all possibilities. Suddenly, let me call the possibility C. Why not? Okay. Then we have in eta, which depends on that C, because in that, okay, what is C? C is like a possible outcome. But eta, the condition that you want, may or may not be fulfilled. That what you want may or may not be happening. So, of all the 3-step random walks that we had, you want only the ones that land up at site 3. Some could have landed at 5, some could have landed at -1. We want to reject those possibilities. We want to count only those which contribute to what you have defined as the event. So, therefore, this will be eta C times the probability of C, because each outcome has its own probability. Eta will count the ones where your criterion is fulfilled. Therefore, when you sum this, you will get a sum over all those configurations in which the event happens. And when you sum over the probabilities of all the ways the event can happen, you will get the probability of the event. This is important. This is a very handy trick. Put in an indicator function, find the average, that will give you the probability. So, this will give you the probability that the event occurs, the event happens, will happen, or whatever you want it. Okay. Point number, this was 9, no? So, we are going to point number 10. Oh, sorry, I am sorry, I rubbed this out. Okay. Number 10. Application of this event idea to a random walk. So, start at the origin, take n steps and ask, is the walker at site M? So, we have to include all possible ways in which the walker can reach M. Okay, so I am becoming a little abstract, I am not putting in numbers like 6 and 3, N and M. Is it okay? So, we have to sum over all histories, all possible histories. So, history will mean I tell you what the walker did. For instance, here is a history of 1, 2, 3, 4, 5, 6, 7, 8 steps. This is a possible history. But there are 2 to the 8 histories, I mean for 8 steps. Each history is equally likely. The probability of each is therefore 1 over 2 raised to 8. In general, 1 over 2 raised to n. Okay, so 1 over 2 to the n, and then I put in my indicator function, if you like, that after n steps, my location coincides with m. Okay, I hope you understand the notation. I am not being very careful with notation. Okay, you could put it, but this is actually equal to Kronecker delta, by the way. So this is equal to, in this case, Kronecker delta of x, n, and m. Is the notation clear? Given a history, you could have had any capital value, x value, but we are picking out the ones that are at m. Okay. So this will give you, of course, the sum over distinct histories in which this reaches m, 1 over 2 to the n times, okay, so this is equal to therefore 1 over 2 to the n times the number of distinct histories. And that we know how to count. That is what we started with on the first day. How many distinct histories are there of n steps, some L's and some R's, such that we land up at site M. Well, if you remember, we changed this to n sub r, the number of right steps and number of left steps, and in that notation, this becomes 1 over 2 to the n, capital N factorial. It is the question of combinations. Combinations in the sense of permutations and combinations, and the relevant answer was n factorial over r factorial times n minus nr factorial, where nr was related in a simple way to m. It was n plus m over 2. For instance, I mean, just if you want to, let me not go and tell you, I was going to spell out one example in detail of histories and so on. But is this point clear? If there is any question, we stop and answer it. Yes. Yes. Is there a question? No. No. Yes? No. You? Yes. No? Okay. You looked a little quizzical. Right. Okay. Fine. Any other question? That row is never asking questions. Huh? Ask. Yeah. Okay. All right. Next point. Point number 11. We are getting there. Simplifications occur if n is large. How do we implement the largeness of m? Well, if we are dealing with factorials, then it is very easy. We use the Stirling approximation. Now, I just presumed that people had heard of Stirling approximation, and I am still going to presume it. Sorry. So, we will assume it. The Stirling approximation is a wonderful approximation. Use it. If you want to calculate factorial of 6, use Stirling. You will find it is very good. If you want to find factorial 2, you will find it is not bad. Try it. One you can do in your head, so I won't ask you to use it. Okay. There is a very nice book called Approximation Methods in Physics by Migdal. It is a slim book, and one of the things he extols is the virtue of the Stirling approximation. Please read it. Okay. Now, So, this is formally done through Stirling, and the result is then for the same thing that we are asking. I have changing notation now a little bit to accord with what we had on the first day, and the answer turns out to be simple. It is 2 per n. In the limit of large n. When n is large, is m also large? Well, typical m is large. Now, this is one place where what you had suggested for using the most probable value will not work. In this case, the typical will be like given well by the standard deviation, the square root of the variance. So, we argued, I am not going to repeat the argument, that the typical value of m is of order root n. But if n goes to infinity, surely square root of n will follow. So, therefore, both m and n are large. You can use the appropriate Stirling formulae and derive this. Point number 12, continuum limit. So, I am going over the things we did and where there were possible questions, and number of people have asked me questions about this continuum limit. Let me just tell you. Okay, so we of course have there are two ways to take a continuum limit. Way A, take large n limit. Typical m also large. Use Stirling. Derive this. Okay, whatever, 1 second. Then pass to the limit in this way. Pass to the continuum limit by setting x continuum limit equal to a times capital M, by setting t equal to n over r, or equivalently, more transparently, n equal to r t, where r is a rate of taking steps. And then of course, if you just look at that thing in the exponent, half m squared over n, by just plain substitution becomes x squared half over a squared r t. Okay, I am just blindly copying from my notes at this point, which is x squared over 4 into half r a squared times t, which I can rewrite as x squared over 4 dt, provided I define the diffusion constant for this problem to be half r a squared. Yeah, sorry for going without stop, but simple. I mean, it's just a question of substitution. Okay, so how am I taking a continuum limit? I am imagining the following. I have a finite lattice spacing, I have a finite rate, okay, but I go to very large time scales and very large x scales. So, on the scale of x, the initial lattice spacing that you started with, it's not 0, but it's very small. So, on the scale of, by the time you've reached meters or perhaps even more, 1 micron is very, very small. And so then x and x, so on the scale of meters, what you call dx would be perhaps 1 centimeter, and that would still include many microns. So you can see that this sort of makes sense. If t is of order seconds and r, or 1 over r is of the order of picoseconds, then this is valid. So you don't have to do anything special, it just happens like this. But the mathematicians sometimes like to say that we will, they don't know about meters and how long you're going to wait and so on, so they would like a limit then and there. Okay, so they talk about a limit. So they take a limit this is the other way. Mathematicians prefer this. A going to 0, r going to infinity, in such a way as to keeping half a squared r equal to d as finite. Okay, and then they will call this object whatever, I mean, even they call it diffusion constant, and so this is the other way to get to it. Now, I see I have exceeded my time, so I think I will just make a few remarks and stop. Fortunately, I have a tutorial tomorrow. Is that correct? Yes. So, the tutorial, in the tutorial I will continue from point 30. Yeah. By the way, in the meantime, I might add more points. Right. It reminds me of something, but I can't tell you. Right. Okay. Yeah. So what I wanted to say is the following. If you all will bear with me for one more minute. It's this form. So far we've been talking and we've been doing things also using the random walk as our model. The result turns out to be this thing which I forgot to tell you, in this limit becomes e to the minus x squared over 4 dt with a normalization which is root 4 pi dt. But you go ahead and you talk to people who do experiments and they find Gaussians which spread in time all the time in many, many, many contexts. So, the notion of diffusion and diffusion constant is very widespread. In many of these applications, it is not so clear or even plausible that you have a single random walker making equal value steps or something like that. So, the answer transcends the model. This answer, model surely leads to the answer, but having this answer does not imply that you started from this model. There might be a whole lot of models, all of which give the same answer. So, this sort of occurrence of something like that is sometimes called universality. So, there is a universality about this answer. How do we know? Just empirically, by measurement. In many places it arises. Also by different people solving slightly different models, they all get the same answer. So, there must be something very special about this answer. We started from a model, that is the best. Start with a detailed proper explanation, get something, then ask, what is the range of validity, and the range of validity is rather large. So, this is the content, this is what I am saying in words, this is the content of the central limit theorem. It sort of occupies a very sort of crown jewel like position in the theory of probability. It is really a remarkable result that many, many, many distributions that you start with, let us say, when you add up variables, those are all distributed according to a Gaussian. As you had asked the other day, does it survive when you make things not independent? Largely yes. Not identically distributed, largely yes. Not independent, well, there are caveats, but very often in proper circumstances still yes. So, it is a very powerful result, and just one has to know it and appreciate it in different contexts. Okay, but now I will stop. Sorry for exceeding the time. Let us go.